The speaker is Martin.
Okay, thank you very much. It's been a pleasure to be here again. So I live in Daejeon, which is like 80 minutes by train from here. So maybe I'm one of the closest participants. And we have seen many participants who have come from very far. Right, and this is joint work with my colleague Klaus Meer at the Technical University of Cottbus in Germany. Software testing and computable analysis. Right, so brief recall, discrete software testing, classical software testing revolves around discrete functions, functions from discrete spaces, such as the space of finite binary strings as domain and codomain. And question typically asked, given an algorithm, does that algorithm really compute that function? Is it correct or not? And discrete means covers many examples, for example, counting perfect matchings in a graph. So suppose somebody sells you an algorithm purporting to count the number of perfect matchings in a graph. Here the output is an integer, right? Counting the number. And integer can be encoded in binary, so that applies to this. And the graph input also can be encoded in binary using adjacency matrix. Another example is return the length of a shortest traveling sales store. Again, integers can be all encoded in binary. So there are many methods that apply to software testing. So to make things a little bit more rigorous towards the science, let's suppose that the function under consideration is computed by a reference algorithm, and we have an input algorithm that purportedly computes the same function. And methods or heuristics are, for example, symbolic execution or black box execution on important inputs. But these are heuristics. For example, what is an important input? This could be input from a benchmark, but what happens on other inputs, no one can tell, right? That's an important part of algorithms. On a different input, it could do something entirely different. So what can we say rigorously as computer scientists, as opposed to engineers, about software testing? Well, testing correctness on one input is semi-decidable or recursively enumerable. Simply simulate the algorithm A on that input. And if the algorithm terminates, compare its output to the value of the algorithm B, reference algorithm B. But it's not decidable. And actually, any non-trivial property of an algorithm is known to be undecidable. That's Rice's theorem, right? And more precisely, it's sigma 0, 1 hard. It's as hard as the halting problem. So sigma 0, 1 refers to the logical notation of an existential quantifier over some countable universe. And some important properties of algorithms are even harder. For example, correctness on all inputs. That's known to be pi 0, 2 complete in the arithmetical hierarchy. So that's equivalent to having universal quantifier, existential quantifier, both over countable universes. So what can we say rigorously about software testing if even the simplest questions are undecidable or even more than undecidable? Well, here's one idea. Let's throw in a promise. Let's promise that the algorithm A terminates on all inputs. So this is the pi 0, 1 property that we know we cannot test. So we just suppose that this is given, granted. What can we then test? Okay. Then correctness on one input becomes decidable. So to simulate the algorithm, and we know that it is going to terminate. Correctness on all inputs will still become undecidable. It's now pi 0, 1. Okay, so it's co-RE. Okay, so how can we further relax the assumptions or throw in further promises? Well, maybe we're only interested in the performance of the algorithm correctness on average inputs. But to make this rigorous, we need to have a probability measure on the domain, and that's not at all clear what is a canonical probability measure on the space of finite strings and why. Another relaxation, approximate correctness doesn't make sense since we're in a discrete space, right? And restricting to compact domains also doesn't make sense because compact subsets of the discrete space are just the finite subsets. So nothing reasonable can be said even with such relaxations. And all this changes when we now move on to continuous software testing. And that's what I want to sell here. Continuous software testing means testing software for continuous problems. So we replace the domain and codomain as discrete spaces, finite binary strings, with subsets of real numbers or real vectors. And now suddenly approximate correctness makes sense because approximating real numbers, they are symmetric, right? Euclidean metric. Also replacing to compact domains, as I already did, makes sense. Unit interval unit cube, for example, non-trivial compact subsets. Also, there's a canonical probability measure on this domain, maybe the Lebesgue measure. So all the things that don't even make sense in the discrete setting now become kind of canonical in the continuous setting. And with continuous, I really mean continuous. I don't mean what people in numerics usually do, floating point numbers, because floating point numbers just forces things from the continuous realm back into the discrete realm and return all the kinds of problems. So I really mean real numbers here. I don't mean rational numbers. I don't mean algebraic numbers. I mean real numbers because that's where all these nice properties really hold. About the promise now seems to become much stronger because now we have uncountably many possible inputs. But as we will see soon, this promise is not really stronger. It's still a pi02 property with emphasis on 0, meaning we're still in first order logic. We don't need to go to a second order logic. We don't need to walk up the analytical hierarchy. So with this promise, then, well, we still need to make this promise, then exact correctness on one input, surprisingly, is undecidable. Remember, in the discrete setting, it was decidable. Exact correctness on all inputs, of course, is even more difficult, but approximate correctness, remember, approximate makes no sense to state, becomes decidable, interestingly. And what I really want to talk about today is about randomized tests for approximate correctness on average, harnessing that here we now have approximation makes sense and average makes sense because we have this Lebesgue probability measure. So that's the goal of this talk. But before going there, what do I really mean with algorithm, right? And algorithm turns out, with algorithm, I mean type 2 machine. So now I need to talk a little bit about models of computation over real numbers, emphasis on real numbers. So there are, can I hide this? Yes. So there are two major models of computation over real numbers. Emphasis on not rational, not algebraic, but really on real numbers. And the one is a Blum-Shoup-Smale model, Blum-Shoup-Smale model, where the real operations, including the real comparison, are considered exact. And this is also underlies, for example, computational geometry. On the other end, there's a model of computation that was introduced actually by Alan Turing himself in the paper where he also introduced his machine, and which was later picked up, for example, by Gregorczyk and many others. For example, this textbook revolves around this model of computation, or this textbook. And this is about approximate computation, in a sense about computing on streams of approximations so that in the limit, the actual result arises. So it's kind of like analytical computing. And that's what computable analysis is about. And these models share some similarities and some important differences. So they all agree that the arithmetic operations on real numbers are computable. But for example, the sine function is computable in the Blum-Schupf-Smale model, but not computable in the stream model. I will explain why in a minute. Conversely, Blum-Schupf-Smale model can only compute rational functions. It only can decide semi-algebraic sets. So transcendental problems like exponential function are intrinsically not tractable by the Blum-Schupf-Smale model, but are by the computable analysis. And so in this talk, focus on the latter, the processing of stream approximation, computable analysis. So in this model, I'm going to show you three definitions. The first one turns out to be unusable, and I'll explain why. And the second and third are going to be equivalent, and this is what our contribution is based on. Okay, so first definition, and remember we're talking about processing real numbers, so any computation must be infinite. It's stream processing, right? Input is an infinite stream, output is an infinite stream. So how do we input a real number? So naive idea, encoding real numbers as binary, right? Infinite binary strings as input on a Turing tape, for example, and output finite infinite binary string also. This is what actually Turing proposed in his 1936, the famous paper, but he soon realized that this is not a good definition, and then he published this correction a few months later. So one first thing to notice about this definition is that equality is undecidable, inequality is semi-decidable, so we just keep comparing the two strings, and once they differ, then we know that the real numbers differ. Basically, but we can never be sure because we need to look up to the last digit, which of course there isn't the last digit. So, but the real trouble with this definition, Turing's first attempt, is that tripling is uncomputable. It's as simple as a function as you can think of. And why is this uncomputable? Let me show you the reason. Proof by contradiction. Suppose there is an algorithm that computes tripling in the binary expansion, and it particularly will be able to triple the fractional number, rational number 1/6 with this binary expansion 0.0010100101. So what is the result of tripling this? This is 1/2. 1/2 has two binary expansions, right? So the algorithm, if it is correct, will have to output one of the two possible binary expansions, either 0.100000 or 0.011111, right? And I'm going to demonstrate that neither of them can be correct by fooling the algorithm. So let's suppose the algorithm outputs the first binary expansion. So at some point it will have to output 0.1. And at that point, that's a finite amount of time. It can have read only finitely many digits of the input. And what we're going to do, we're going to change the input beyond the part that it has read so far. So the algorithm will not notice and will produce the same output as before. What we're going to do is we're going to change 1 into zeros. And then, of course, tripling that will be strictly less than 1/2, and outputting 0.1 will be actually error by the algorithm. So that's not possible. What about the second case? Suppose the algorithm outputs 0.01111. Then again, the 0.0 will be output after finite time. Within this finite time, the algorithm could have read only finitely many initial digits, and now we're going to change the input beyond that part, and the algorithm will still keep outputting 0.0, but now tripling this number, which is strictly greater than 1/6, must be strictly greater than 1/2, and so this is also an error. So tripling in binary expansion is not possible. And so what Turing did, change the definition, abandon this, and considered a new definition, namely, well, this is one equivalent to Turing's revised definition, is input and output are a sequence of dyadic rational approximations. So rational numbers, but the denominators are integers of powers of 2 up to guaranteed error 2 to the minus m, when the denominator is 2 to the plus m. Okay, input and output a similar sequence. So again, stream input, stream output. Now that's a much better definition. Well, equality is still undecidable, inequality is still semi-decidable, but now all the real functions that you can think of, the continuous ones turn out to be computable, and this is kind of a formalization of arbitrary precision numerics, right? A sequence of computation with higher and higher precision. Could also be regarded as a formalization of domain theory. And yeah, even so transcendental functions are now computable, but still any computable function must be continuous, so no jumps, Natura non facit saltus. And now we're in business to also introduce complexity, right? So far, I've only talked about computability. This is still a short course on computable analysis for you. Complexity, well, traditionally complexity is defined in terms of the number of computational steps depending on the input length. But remember, the input here is infinite. Output is also infinite, so input length is not a good complexity parameter. What is a better complexity parameter? Output precision. How many steps does it take to output the nth output approximation up to error 2 to the minus n, regardless of the input and regardless of how the input is encoded? Note that in the binary expansion, every real number had 1 or 2 expansions. Here, in this sense, with a binary dyadic approximation, every real number has uncountably many ways of encoding it as a sequence of dyadic approximations. So that's uncountably many possible inputs for every given x and uncountably many x. But the running time must depend only on the output precision. That's a common definition of complexity here. And then the first folklore theorem strengthens. So first folklore theorem says any qualitatively computable function must be qualitatively continuous. The strengthening says that any function computable in time t of n will have modulus t of n. So modulus t of n means whenever the two inputs, real numbers, are closer than 2 to the minus n, then the values will be closer than 2 to the minus 2 to the minus n. And that's an important part for the for testing software, because remember, in the discrete case, knowing only what happens on one input doesn't tell anything about any other input. But here, knowing what happens on one input tells something that on close by inputs, the resulting value will also be close by. Okay, and that's what we're going to harness in the continuous setting. So I mentioned 3 models of computation. First was binary, we expand that. Second was sequence of dyadic rational approximation, that's good. And this is the third one, which is equivalent to the second one, which will turn out to have some benefits. And that's, again, encoding real numbers input and output by binary sequence, but not by 0, 1, but also by using the binary digit -1. So that's sometimes called the signed binary expansion. So you see here -1 on the input and -1 also on the output sequence. And again, every real number now has uncountably many such sequences representing it, converging to it in this series. This is the signed binary expansion, and this is equivalent to the one I've mentioned previously. And this will turn out to have some structural benefits. Okay, so now I've introduced the computable analysis to you. And some first consequences is that here is an example of a function, which is an explicit function, which is computable in exponential time, but not in polynomial time. Because this function is continuous, it looks like it has a singularity at pole at x equals 0, but it's a removable singularity. In fact, it can be extended continuously to 0 with value 0, but it is exponentially steep at 0. It has an exponential modulus of continuity, no polynomial. And then according to the second fact, folklore effect, it cannot be computed in polynomial time, can be computed in exponential time. Now, returning to the issue of software testing, recall our promise. And as I said, superficially, it looks like a promise made on uncountably many inputs. When I mean termination, I mean do now some currying, right? Instead of asking to output an infinite sequence, we input an additional index parameter and say, give me the nth output approximation only and terminate. So then the promise makes sense. And folklore theme in computable analysis said, if an algorithm computes a function and terminates on all input, then it admits a computable time bound, which depends only on the output precision and not on the input, or which, if you recall it from the discrete setting, that's trivial, right? In the discrete setting, n means consider only inputs of length up to n, of which there are finitely many. If the algorithm terminates on all these finitely many inputs, take the maximum, and that's a runtime bound. But here, remember, that's not at all the definition. Here we have uncountably many possible inputs. So in order to prove that folklore theorem, in the continuous case, compactness argument comes in, and that also, this compactness argument is what lets us prove that this promise is still pi 0, 2. It's still in the arithmetic hierarchy, not in the analytical hierarchy. Okay, so finally continuous software testing. What can we do and what we cannot do? So approximate correctness of all inputs now becomes decidable. Here's a way of testing approximate correctness on all inputs. Simply approximate the function or run the algorithm on a grid of spacing 2 to the minus t of n plus 1. Remember, t is the modulus of continuity or the runtime bound that exists and can be computed by the promise. And then because of this modulus of continuity on all points that are not in the grid, but sufficiently close, the values cannot differ by much, right? So doing that on this grid, that's a deterministic algorithm. But our goal is to have a randomized test for correctness on average, and this randomized test simply replaces the grid of 2 to the t of n plus 1 points with a grid with 2 to the delta t of n plus 1 points. And then from that, it follows that if the algorithm is correct on this smaller grid, then it is correct on a subset, at least on a subset of measure delta of the domain. So that's our randomized test for approximate correctness on average, something that, as you recall, cannot even be defined or does not make sense in the discrete setting, but here in the continuous setting, it works out. What I mean, by the way, by approximate correctness on average, it means when the algorithm reports yes, it is correct, then the set of points where the actual functions differ by more than 2 times epsilon, this set has small measure, less than 2 times delta. And where the algorithm says no, then the set where the function values differ by more than epsilon over 2 has measure more than delta over 2. And you see that these two cases have an overlap, and that's deliberate and that's important. Right? So factor 2 in the error bound, 2 times epsilon versus epsilon over 2. and factor 2 in the measure of the set where the functions differ by more than that. Right. Now, if you have paid close attention, you might ask a question. So when I say random points in the real unit interval, what do you mean with that? Well, one interpretation is that take a random real number according to the Lebesgue measure, right? Take a random number, find a signed digit sequence that represents that number, and then run the algorithm on that particular sequence. But that does not say anything about the behavior of that algorithm on a different signed digit sequence that represents the same real number, right? So another interpretation is directly sample a signed digit sequence and run the algorithm on that with a suitable probability distribution on this space of signed digit sequences. So the first may be called extensional sampling, and the second intensional sampling. And both are not equivalent, but they become equivalent if we throw in another promise, namely the promise that the algorithm already is extensional, meaning it maps different signed digit sequences for the same x to possibly different signed digit sequence for the same y g of x. So that's another promise that we consider. How difficult is that promise? That's another pi02 promise. So logically, still first order logic, but also as hard as the first promise that the algorithm terminates on all inputs. What does not make sense, and this is the reason why we consider this signed digit sequences not the sequence of dyadic rational approximations, is it's very hard to define a probability measure on this sequence of dyadic rational approximation, because those dyadic rational approximation sequences that converge to a real number are a zero set among all such sequences. And so take a probability distribution on the whole space and then restricting that, you cannot do that because it's a zero set. So that's the reason why we consider these signed digit sequences, they form a dense, a fat set. Okay, I'm running out of time, so let me speed up. So this was about testing correctness, whether a given algorithm computes a fixed real function given by a reference algorithm. Our second contribution is about testing whether a given algorithm computes a function from a class, from a fixed class of functions. So consider a class of functions from the unit interval to real, and does a given algorithm compute a function from this class approximately, and the class we're particularly interested in is the class of univariate polynomials. Now this setting, again, doesn't make sense. Why not? Because the univariate polynomials are dense, right? So every continuous real function is arbitrarily close to some suitable univariate polynomial, so the answer will always be yes. So how can we make a sense of this? By introducing a degree restriction. So now the question is, does a given algorithm compute some polynomial of degree less than d? And yes, as time is running short, let me just say that we take an algorithm which is maybe well known from the BSS model, and we adapt this to the stream model by using a relaxation of epsilon nets, right? So from learning theory, Vapnik-Chevonenkis dimension, but now with approximate learning. And the details are in the paper, so let me skip over that and just proceed to the final conclusion slide. So discrete software testing, most things cannot be done, even with the promise that the algorithm terminates on all inputs, pi02 promise. Correctness on one input is trivially decidable. Correctness on all inputs is still undecidable. Relaxations like approximate correctness make no sense. Relaxation like restricting compact domains is trivial. That's the same as a single input, finitely many. Correctness on average doesn't make sense. Continuous software testing, on the other hand, many of the relaxations make sense. Replace discrete spaces with real spaces. Then it makes sense to ask about approximate correctness. It makes sense to restrict to compact domains and harness that, of course. It makes sense to ask about correctness on average with a canonical probability measure. Exact correctness on one input turns out to be undecidable. Approximate correctness on all inputs turns out to be decidable. The promises is still pi01 promise. Algorithm now means this type 2 machine from computable analysis. And we also came up with an additional promise that the algorithm is extensional or not. That makes a difference whether we sample real numbers or whether we sample signed digit expansions. So that's all I wanted to say, and thanks for your attention, and I'm here for questions.
Thank you.